I like to move it, move it. I like to move it, move it. You like to move it. I like to move it, move it. I like to move it, move it. I like to move it, move it. You like to move it. I like to move it, move it. I like to move it, move it. I like to move it.
Newsflash, things move. I'm sure you're aware of this, but how do they move? Think of all the different ways in which things move. They can move fast, they can move slow, they can jump, they can vibrate. The list goes on and on and on. So since we're a class and physics involves a lot of math and drawing, how can we show this on paper? The simple answer is with a motion diagram. So a motion diagram is just a series of pictures that show something moving at equal time intervals. You can look at this picture up here of this skateboarder, and he's moving with a constant speed. So the dots are evenly spaced, and then he's arriving at a certain distance represented by x. So a particle model of this would be the same thing with dots instead of pictures. So if you can see on the screen, there's dots up there underneath his pictures. The motion diagram is just the picture, and the particle model is just the dots. Another Physics 101 lesson, scalars versus vectors. These are already numbers that you are familiar with. They were just putting a name to them. So a scalar quantity has only magnitude. Magnitude is size or quantity. So a scalar quantity would be something like length, mass, density, pressure, temperature, all of these things that you already know about. A vector quantity has both magnitude and direction. So it's got a size or a quantity, and it's saying which direction it's going. Since we're talking about speed and velocity, usually when things move, they move in certain directions. So we call velocity a vector quantity, and that just means that we're indicating that something is moving at a certain speed and it's going in a certain direction. Vectors in math. So these are the same as regular addition and subtraction, but we add direction. It's basically like negative and positive. We call the answer a resultant. So basically, in these examples up here, you've got somebody maybe moving 3 meters east, and then they move another 7 meters east, and they've moved a total of 10 meters east. In the second example, you've got somebody moving 10 meters east, 3 meters in the opposite direction west. When you add them up, you would get 7 meters east, because that's the higher number in that equation. And the last one, it works the same in up or down. So we can say that this person moved 4 meters north, and then they moved another 4 meters north, and their resultant would be 8 meters north. Displacement. So displacement is kind of like distance, except for it's only concerned with how far you traveled from your original position, okay? So if I'm traveling somewhere and I arrive back in the same spot, I have not been displaced because I arrived back in that same spot. If you look at this graphic down here in the lower right-hand corner, you can see that displacement is kind of just point A to point B. It doesn't matter where you went in between. So if you were going, let's say from school to the park, you decided to stop at Burger King, and then you went to 7-Eleven, and you had all of these munchie stops in between, but then you eventually went to the park, your displacement would just be the distance that it took you to get from school to the park, but not to 7-Eleven or Burger King. In our physics math equations, displacement is represented by the change in x. That little triangle is called a Greek delta, and it stands again for the change in. So anytime you see that, you can see like delta x, that's what it is, the change in x, or the change in position. So x again equals position. Position time graphs. You can basically think of this as an XY chart that you're used to doing in math. So time is your independent variable, and position is your dependent variable. So anytime you do a position time graph, make sure that the time goes on the bottom. And then over to the left, these are just the XY chart that goes along with this graph. So you can see that at 2 seconds, he's gone 4 meters. At 4 seconds, he's gone 8 meters. It's just a really easy way to tell where somebody is at a certain time. So if I asked you, find Peter Parker's distance at time 8, you could look at this graph and say, that looks a little bit above the 15, so I think he's gone 16 meters. Pretty easy. Speed versus velocity. I've kind of used these terms already before in this presentation. This is just clarification as to what I am talking about. Speed is the same thing as velocity, except that velocity, again, is a vector and it indicates direction. So this is kind of like how fast you're going, that would be speed, versus how fast and in which direction, that would be velocity. When you write this, you would say 50 meters per second for speed versus 50 meters per second east for velocity. Instantaneous speed. The speed or velocity you're going at any given moment. This is represented by the letter V, and this would be just a single point on a graph or a diagram. Cops usually pull you over for your instantaneous speed. They don't take your average speed and decide that you were going way too fast. They can point their radar at you and find out you're going 100 miles an hour at one point on your drive to school when you're supposed to be going 35. Average velocity. This is the flip side of that. Average velocity is just how fast you get from point to point. This is represented by V with a little line over it, and this would be the line on a graph or a diagram, so the line in between points. You're familiar with the tortoise and the hare, I hope. This is basically the story of a tortoise and hare taking a race. The hare falls asleep, and the tortoise wins the race. So if you think about this in terms of average velocity and instantaneous velocity, you could say that the hare had a higher instantaneous velocity, but the tortoise had the higher average velocity because he kept going and he was able to win the race. Calculating average velocity. So this is the equation that you need to do this. You've got the average velocity equals the change in position over the change in time. That's what those letters stand for. If you spell it out piece by piece, you get final position minus the initial position divided by the final time minus the initial time. Usually in our equations, the initial time and the initial position are just going to be 0, so it kind of like just simplifies to position divided by time. So if you look at those little letters that I was saying, final position, initial position, that's what those little subtext letters are. Just read them. They kind of clarify what they're talking about in physics, because sometimes we have so many terms that we're not sure what we're talking about. So always read the subtext, but don't math the subtext. So that doesn't mean anything. You're not supposed to put a letter in for it. It just tells you which position you're talking about. So here's an example. What is my average velocity if I traveled 10 meters west in 10 seconds? So it would take my change in position, which is basically 10 meters because I started at 0 meters. And then I would divide that by 10 seconds because I also started at 0 seconds. That would equal 1 meter per second west. The triangle of power. Not that triangle of power, and not that triangle of power. Ooh, this triangle of power. This is basically an easy formula finder. You cover up the variable you want to know, then you read what's left. The horizontal line stands for division, and the vertical line with letters side by side stands for multiplication. So if I want to find out what velocity is, I already know that it equals position divided by time. That's how I filled out this triangle. I could cover up the V, and then I would notice that, hey, the x and t are still left. There's a horizontal line in between. That means I should divide them. And there you go, you've got velocity. To find time, you cover up time and you realize, hey, there's an x and a v there. There's a horizontal line in between. I divide them. So you get time equals position divided by velocity. Lastly, if I want to find position, I cover up the x, and I notice the v and t are right next to each other, which means multiplication. And so I get that position equals velocity times time. Pretty easy. You can use this with almost all of our formulas. and it will kind of simplify a lot of the math that you're doing if you want to use this. Looking at graphs again. So here's where that y equals mx plus b that you've been working on so hard in the past couple of years of your life comes in handy. So the slope of your line is the velocity of your object. So over here I've got my x-y chart, which you're familiar with already. And then I also have this slope point equation that you may or may not be familiar with. So slope equals the change in y over the change of x, which also equals y2 minus y1 over x2 minus x1. You remember that? That's how you find the slope of the line when you're given points. And here we go. Velocity equals the change in x over the change in t. So that's position over time again. And then you've got your final position minus your initial position over the final time minus the initial time. These are exactly the same. So if you want to find velocity, all you have to do is find the slope of your line. More graphs. Here's another position time graph. You've got distance in meters up on the left and time down on the bottom. This is you playing Mario Kart with your grandma. She doesn't know what she's doing, but she's cool enough to try. So you start off, and she doesn't understand what button to press, so she's just sitting there. You can see that on the left-hand side, the distance is not raising at this part of the line. Next, you tell her, hey grandma, press A, it's the A button, and she figures it out and she speeds up for a little bit. But then she gets confused and stops again. Here, she's decided to go backwards. She's totally pressing the wrong button, and she's going back the way she came. Down here, you can see that the graph extends below the 0 point. So that's where she started, and she is now going past where she started in the backwards direction. Finally, she figures it out, and she fires a blue shell, and she starts winning, and she almost beats you at the end. Here's your line. You're moving at a constant velocity. You can see there's no fluctuation in your line. Lastly, DIY. Use what you've just learned to complete your practice assignments. I'll be posting a few examples worked out for you guys as well if there's any confusion. Also, bring it to class. Ask me questions if you don't get it. That's what I'm here for.